So we decided during the break that we should go over the input for the last example that we looked at, since we haven't actually gone over an Mplus input yet. And that was the case example. And that example, as I mentioned, people are randomly assigned to the treatment and control groups. And that's the basic trick that makes this modeling work. So if you don't have random assignment, then this would not be a model that's appropriate. So let me just talk a little bit about the Mplus language, since we haven't done that yet. And we do not have a diagrammer to put your model in with a diagram, basically based on the fact that Mplus has so many complex models that when we looked into doing that, it just seemed almost impossible, and that it was harder to do the diagram than it is to do the language. So we decided to stick with that. But basically, Mplus has 9 commands. For example, title, data, variable, analysis, model. The data command tells us where the data is. So the file option names the data set, and there are various other options in the data command. For example, if you have fixed format data and things like that. The variable command tells us all about the variables. The names option names the variables in the data set in the order that they appear in the data set, so we know where to find the information for each variable. We have a use variables option in the variable command, where we can subset the variables from the data set. If you don't want to use all the variables in the data set in the analysis, you can use the use variables option. And there are many, many other options. For example, the missing option allows you to specify missing value flags. The options that are important here for the mixture modeling are the classes option. And here we use the classes option to name the categorical dependent variable. So the observed variables get their names from the names option. But for latent variables, we use the by option in the model command to give names to continuous latent variables, but we use the classes option in the variable command to give a name, C. C is the name of the categorical latent variable. It could be cat, dog, whatever. But after the equal sign, you give the name of the categorical latent variable, and in parentheses, you say how many classes it has. So here we're saying that we have one categorical latent variable in our model, C, and it has 2 classes. Now, the training option is used to specify which variables contain training variable information. Like I talked about, that the training variables say which classes a person is allowed to be in. So treatment compliers were only allowed to be in the complier class. Non-compliers were only allowed to be in the non-complier class. But for the control group, since we didn't know whether they were compliers or non-compliers, they could be in either class. So training equals says that C1 and C2 are the training variables. The analysis command tells about what type of analysis we're doing. So here we say type equals mixture to say that we're doing a mixture model. And in the model command, it specifies the model that's going to be estimated. And when we're doing mixture modeling, we have the overall part of the model, which specifies the general model. And then we can also have class-specific parts. So for example, the percent C number sign 2% is saying that the statements following that are going to be class-specific statements for class 2. The C here is the name of the categorical latent variable. The number sign is just the number of the class, and 2 means class 2. So percent C number 1% would mean that the statements following are about class 1. So the model command is basically the most important part because it specifies the model to be estimated. And then we have an output command where we can ask for extra output in addition to the output that comes as the default. So if you look in the overall command, you'll see that we have 2 on statements, capital on in the first line and the second line. The first on statement specifies the regression of the continuous depression item on the 3 covariates. So you just say depression, and on is short for regressed on. So it's depression, regressed on, and then you have the three covariates, TX, risk, and depth base. So that specifies the linear regression because depression is a continuous variable. C number 1 on age, education, etc., is this regression on the right screen, C on this whole block of variables. And that's a multinomial logistic regression. You can just say C without number 1 on if you are doing the full multinomial logistic regression. So if you said C on versus C number 1 on, it would be the same thing. So we've added some shorthand language. So here we have that, and then you see in the class 2, so depression on treatment is in the overall model, which would mean that it would be in both, everything in the overall model is in both classes. The class-specific part just changes the overall model for that class. So as we mentioned, we wanted to have the depression for the complier class, or the non-complier class rather. So class 2 is non-compliers, depression on treatment at 0. The little at sign means fixed at. So we're saying that the regression coefficient in depression on treatment is fixed to 0 for class 2, the non-complier class. So that's an explanation of the input. And then just briefly, we're going to be going through a lot of output as the days go on. So we won't go over this first part and the second part because we'll be doing that. But instead, here's the model results for class 1. Now the way we give the output, the first column is the parameter estimate. The second column is the standard error of the parameter estimate. And the third column is the ratio. So that's like a z-score. So we would be looking for significance values greater than the absolute value 1.96. So what are we interested in? The important thing here is depression on treatment. This is the class of compliers. So these are compliers only, and that depression on treatment represents the effect we're interested in. We see it's significant, it's negative, so the treatment is effective in that it reduces the depression score of that continuous variable, which is what we want. We want people to be less depressed after they receive treatment. And that is equivalent to, so that's what we want. Had we not done this analysis, had we mixed the compliers and non-compliers together, I think that's the ITT, then we would not have found an effect. So, here we're able to sort the data in such a way that we actually compare what we're interested in. And then one other part of the output is the C regressed on everything. So we want to understand who are these compliers and who are these non-compliers? Who are these people? And I think it was only 54% of the people took the treatment. So we only had 54% compliers in this study. So it was really important to know who they are. So as we can see here, they seem to be older, more educated, the significance here, more motivated, and less assertive, I guess. And so you can see here which are significant from the third column. So that will help you understand something about your study. And for example, if you did this study and then you understand maybe in the future you could have a treatment that would appeal to more people, so more than 54% complied. So this is what you can learn from this. And then I think it's your turn.
Just wanted to connect what Linda just talked about with another field of statistics. At this point, Linda's using this example of case modeling, non-compliance modeling, to illustrate regression mixture analysis, just plain regression mixture analysis. But that topic really fits into a much bigger picture, which is described in this statistical paper, Angrist, Imbens, and Don Rubin in JASA, where this is put into the context of causal inference, which you have on slide 59. And causal inference to statisticians means something quite different than what's considered in, say, structural equation modeling. They talk about terms like potential outcomes and principal stratification, and that's all described in articles like this one and also in Boole-Joe's papers. Interestingly, though, that leads to finite mixture or latent class modeling, as we have seen. So when you read this literature, Angrist, Imbens, and Rubin, or Little and Yao, you will not see these model diagrams that tie directly into regression mixture analysis that we have shown. It seems more complex, I would say. But you should remember then that you have this bridge, this link between the two in these notes. So I will not take the time to go through this now, but I just point out to you that there is this connection, and you may want to study it if you work with randomized trials where you have a non-compliance. And it's actually more generally applicable than that when you talk about principal stratification. This slide talks about potential outcomes. I'll just say that much, but I won't talk about what it is. And this then refers to the JASA paper, where it had to do with individuals being allocated to participate in the Vietnam War. So there's a whole literature on this, causal effects. And in fact, if you look at slide 64, you may just want to note on slide 64, I know you obviously don't have time to think through this, but they have a 2x2 table here, a 2x2 table at the top of slide 64, which corresponds to 4 latent classes. And we have been working with only 2 of those 4. So we have a very simplified situation here. Essentially, we've talked about the never takers and the compliers, but there are also defiers and always takers. Always takers, for instance, in this case means those who were not invited to take the treatment took the treatment anyway, like individuals who take the medicine even when they're not assigned to take the medicine. So I just want you to be aware of this literature, and this slide 65, you can just note that it's an attempt to tie the statistical literature to the mixture applications that we are talking about here. Also, by way of introduction, when we talk about growth mixture modeling tomorrow, I should say that I have just finished a paper on growth mixture modeling using the causal inference thinking, using the potential outcomes principal stratification in a situation where you do not deal with non-compliance, but it's used in a more general setting when it comes to analyzing antidepressants in the presence of placebo response. So if you work with randomized trials, I would really recommend you to dig into the causal inference literature. And there are many good short courses on that given in various places in Europe and elsewhere. So now let's take a deep breath and start with what I would consider a key topic of today, which gives a good basis for the rest of our days together. And that's latent class analysis. And it is then in the context of having not only one dependent variable, but a set of dependent variables from a measurement instrument that you have designed. And to just introduce that as quickly as possible, but still in an understandable way, I'm going to talk about models in terms of a picture that has a model diagram on the right and a more substantively oriented picture on the left. So if you start with the left part here and start with the x-axis, we have 4 items here. And this is in the context of ADHD, attention deficit hyperactivity research, where you study children's inattentiveness or inattention and their hyperactivity. And here you have an example of 4 items. There are 4 items here on the x-axis. Inattentiveness items 1, inattentiveness item 2, hyperactivity item 1, and hyperactivity item 2. In actual practice, then, there are many, many more items. The instrument that we're going to talk about later has 9 items of each of the 2 types. On the y-axis, you have the probability, because these items are dichotomously scored. Either you endorse the item, yes, this pertains to my child, or to this child, or no, it does not pertain to this child. So you talk about the probability of endorsing an item. And for instance, here, we're going to look at a profile. We're going to talk about item profiles. Here's a profile of individuals who are in class 4, and they have a low probability relative to the other classes, low probability of endorsing any one of these 4 items. So we can think of class 4 as the normative class. If we have a general population sample, the probability of fulfilling these items is fairly low for all kinds of items of this kind. So you have a low profile, as opposed to, say, class 1, where the profile is high, the probability is high to endorse either one of these or all of these items. If we had continuous outcomes, the y-axis would be the means of the items instead of the probabilities. If we worked with counts, the y-axis would be the rate or the log rate. So all of these possibilities of outcomes are possible in latent class analysis settings. And then we have a class 3. It's a class where where the child only shows inattentiveness, high probability of that, but doesn't show hyperactivity, low probability of that. And class 2 is the reverse situation, low probability of inattention and high probability for hyperactivity. That's probably a more rare class, because if you show hyperactivity, you tend to also show inattentiveness. So the question is what the percentage or probability is of being in class 2. So you see here then already that there are 2 kinds of parameters here. Corresponding to structural equation modeling parameters are structural parameters and measurement parameters. Structural parameters describe the population of the people. Measurement parameters describe the variables. So structural parameters describe the people. Measurement parameters describe the variables. So here, the structural parameters would be the class probabilities. How many people do we have in these 4 classes? Distribution of people over these 4 classes. And the measurement parameters are these probabilities. So for instance, if you look at item hyperactivity 2 here, the probability of endorsing that item is about 0.2 if you're in class 4, about 0.4 if you're in class 3, 0.8 if you're in class 2, and 0.9 if you're in class 1. So this one item has 4 different probability parameters connected to it. We're going to call them conditional item probability parameters. Conditional item probability parameters. And that's a measurement parameter describing the items. So for each item here, we have 4 probabilities, 4 parameters. So with 4 items and 4 classes, it would be 16 parameters here. Whereas the structural parameters are, well, there are 4 probabilities, but they have to sum to 1, so it's really only 3 different parameters. So that's the substantive aspect of the story. And you're interested in sorting people into, based on their profile of how they answer, we're interested in sorting people into classes, and then also estimating the parameters of the model, of course. So usually we first estimate the parameters of the model, the class probabilities and the conditional item probabilities, and then we try to estimate the person's most likely class membership. We're going to say that many times, so you don't have to pay too much attention to it right now. Now, this looks very simple, of course, like a very clean structure, but these are averages. These are the average. These are the item probabilities within class. The data, of course, is much messier, a bunch of zeros and ones. So it's very hard to see the structure in the data without doing the analysis. And of course, the result may not look this clean at all. They can look quite more complex, particularly if you have not designed your items well. If you have not designed your items well to capture these classes. In any case, the model picture, just to connect it with what we talked about before the break, now we have multivariate dependent response. We have 4 dependent variables instead of 1. We have our latent class variable here, which has 4 possible categories to it. And we say that latent class membership influences the response on each of these 4. Influencing it meaning that you have different response probability for say, item hyperactivity 2, depending on which class you're in. That's what we just talked about there. Now, given that C influences these 4 items, you also have then the correlation between the items explained by C, so that they only correlate because they're all influenced by C. And that's the conditional independence assumption. And that we will relax this afternoon. We'll relax it just before dinner. So now you can also then, so this is the measurement part of the model here that I'm pointing to, measurement part. Measurement being the relationship between the observed and the latent. And then the structural part has to do with how many people are in the classes. And then you can also ask, well, what kind of background variables influence, what kind of background variables X influence the probability of being in these classes? And this then is a structural part of the model. You have the intercept of C and the regression slopes here. And Linda just alluded to that very briefly. When you have C being a polynomous variable in many categories, and when the categories are unordered, we would think of C as a nominal variable, not ordered necessarily. And when we have regression of an unordered polynomous variable on X's, that's called a multinomial logistic regression. Multinomial logistic regression, as opposed to the logistic regression we talked about before for binary responses. But we will show you the formulas of that a little bit later. Now we just introduce it as a possibility. So we can see then what kind of characteristics of the individual child influences being in one of these classes. So for instance, if one of the parents had ADHD, then it's more likely that the child will be in one of the ADHD classes, say 1, as opposed to being in class 4. Now, you may also be interested in direct effects, which we're going to talk about later on after lunch. That is, you can have an effect of, say, genetic loading in your family, not only on class membership, but more directly on to hyperactivity too. And again, this connects with many different kinds of modeling thinking. For instance, this can be viewed as a diff, an IRT diff, item response theory, differential item functioning, item bias. For instance, if this is gender, this could say that the probability of endorsing this item is influenced not only by the class you're in, but it is also different for different genders. So there is then a measurement difference for the 2 genders. So that could be, potentially that could be a problem in that you do not have measurement invariance. You do not have measurement invariance across gender. Or it could be really interesting, for instance, if this is a genetic loading variable, family history of ADHD, has a specific influence on hyperactivity too. That is, that item is specifically sensitive to capture genetic influence. So that could be a very interesting path. Now, much of this has been described by the classic book from 1968 by Larsfeld and Henry, by Leo Goodman's work in Sociological and Statistical Journal, by Cliff Clogg's work in the same journals, and Mitch Dayton and George McReady in the educational settings. And we're going to take several examples of this. We're going to look at cross-sectional data first, where we have multiple items measuring a construct. In this case, it was 4. And the hypothesized construct it's reasonable from a substantive point of view to represent it as a latent class variable. And the aim is to identify items that indicate classes well. So by that I mean that this item, you have a big discrepancy in probability between classes 3 and 4 on the one hand and classes 1 and 2. So there's a big jump here. So it discriminates between those two sets of classes. The probabilities are not the same across the classes. That's an item that works well. You want to estimate the class probabilities that we talk about, and you want to relate class probabilities to covariates, which was this arrow here. And then once you've done that, you want to classify individuals into classes. That last step then corresponds to what structural equation modeling and factor analysis people talk about as factor score estimation. Factor score estimation for categorical variables concerns estimating the probability of being in a given class for a given person. And we will call those posterior probabilities, class-specific and individual-specific posterior probabilities in the applications. So I think Linda's going to talk about diagnostic criteria for alcohol dependence in the national sample, and she's going to talk about antisocial behavior measured in a US national sample as well. But before that, let's talk about some more theory that we need. So now it will be a little theory heavy, but it will be useful for us for all of our models that we're going to talk about today and tomorrow and Monday and Tuesday. So if we start on your left screen, we have a generic situation here with 3 dichotomous items and a categorical latent variable with k classes, And first of all, we're interested in, say, the probability for a certain item, one of the 3 items. And that is then written in this formula. And again, this formula can be, you can just think of it as having 2 parts. Probability of the class membership, the structural parameter, describing the people distribution. And then this part that I'm circling now, the conditional item probabilities, probability of endorsing the item, conditional on the class. So this is the measurement parameters appear here, and the structural parameter there. And then you sum over the classes to get the marginal probability here. So you can answer u equals 1 when you are in many different classes. So you have to get the total sum of u equals 1, you have to sum over the classes. And then you have the joint probability of all 3 u's, assuming that they are independent, given C, meaning that C is the only way they correlate, there is no residual correlation. Then this is the expression for the joint probability of those U variables, and it becomes a product of the univariate probabilities because of this independence assumption. Anyway, now posterior probabilities we talked about. These probabilities that we talk about here, probability of U given C is probability of observing something given the latent variable. Now we're going to go the other way. Now we've estimated all these parameters. Now we're interested in what's the probability of a person being in class K given that person's response on the observed variables. And by the magic of statistics via the so-called Bayes theorem, that posterior probability can be expressed in terms of the model expression up in the numerator here. This numerator is the same as you see bottom left there, divided by this marginal probability for the U's. if you multiply the denominator on the right with what you have on the left, they say the same thing, so the equality is true. That's Bayes' theorem. And that is used in two ways. Why do we bring in Bayes here? You know, there are two branches of statistics. There are frequentist statistics that do things like maximum likelihood estimation. And then there's Bayesian statistics that thinks of parameters as random variables. We're staying in maximum likelihood, but during the frequentist approach here, during the maximum likelihood estimation, using the so-called EM algorithm, these posterior probabilities play a role because EM is a technique that tries to reach the maximum likelihood estimates, parameter estimates that makes the likelihood as big as possible given the data. And that's very often used when you have missing data. And in fact, C, the latent variable C, is seen as a missing data phenomenon. And EM acts as if we knew the latent variable, the missing variable, if we knew its values, the problem would be very easy to solve. So then if you don't know it, like we have here, let's try to come up with an approximation for it. So you have the expectation step, which comes up with an approximation for the latent variables and their relationship to the observed. And once you have that approximation, you can just do, if you knew C, if C is known up to an approximation, then this is just a bunch of logistic regressions, right? Which we know how to do already. So the M step is to estimate those parameters. And once we have estimated them in the M step, we can go back and do a better E step, a better approximation of the latent variable. And with that better approximation of the latent variable, we can do a better M step. So you go back and forth between these until it converges and you get the maximum likelihood estimates. But in this E step, you work with posterior probabilities, which are up here. So they're used in the computation in the EM algorithm for maximum likelihood estimation, but they're also used at the end. Once you have the maximum likelihood estimate, they're used to compute individuals' likely class membership, to do the so-called factor score step and place them in their most likely class. So that was a mouthful, right? But let's then take it a little bit further here, and then Linda will come with an example. So I'm going to talk about, before lunch, we're going to talk about what I would think of as exploratory latent class analysis. If you make the analogy with factor analysis, we have exploratory factor analysis and confirmatory factor analysis. Now we're going to talk about exploratory factor analysis. So, sorry, we're going to talk about exploratory latent class analysis. So H0 is the hypothesis of our zero model, that is the model that we're interested in, the LCA model, is the H0 model. With K classes and R binary U's, how many parameters does it have? Well, K minus 1 structural parameters, because there are K classes, but the probability is summed to 1, so we subtract 1. And for each class, we have R item probabilities, so we will have K times R. Now, H1, on the other hand, is the, in line with structural equation modeling, it's the unrestricted model, not the LCA model, but it's an unrestricted model. And the unrestricted counterpart here for categorical outcomes is the so-called multinomial distribution, the multinomial distribution. So, for instance, if you have two variables that are binary, you have a 2-by-2 table, so it has 4 cells. So the multinomial distribution just describes the probabilities of those 4 cells. So for 4 cells, you need 3 parameters to make it totally unrestricted, right? That's the multinomial. So multinomial is sort of the categorical counterpart to the normal distribution for continuous. So with binary variables, R binary variables, you get 2 to the power of R. So with 5 variables, you have 2 to the power of 5. How many are that? You figure it out. 32? Minus 1. So that's the number of parameters. So then you can ask yourself, well, what if we have three U variables, three binary variables, and want to try to extract two classes? Well, then you have the same number of parameters in H1 and in H0. Both cases you have 7, right? 2 times 2 times 2 is 2 times 2 is 4 times 8 minus 1 is 7. And for H0 you have 2 minus 1 here, and 2 times 3 is 6. You have 7. So you have the same number of parameters in H1 and H0, so you cannot tell the two models apart. And one way of putting that is that the degrees of freedom is 0. Another way of saying it is that that model is just identified. And another way of saying it is that that model is saturated if you come from sociology. So it cannot be rejected. You cannot say that H1 fits significantly better than H0 because they're one and the same model. And you want to be able, so that's not a good thing. Well, that sounds like a good thing, right? You cannot reject your model. It's not a good thing. You want to give yourself a chance of rejecting your models, because you probably know from working with data analysis that most often you're wrong. So you want to be able to refute your ideas. So if you're interested in teasing out 4 classes, you better design your measurement instrument to have at least 4 indicators U. Then you get 6 degrees of freedom. Number of parameters in H1 is 6 more than in H0. I'll tie this to chi-square testing in a second. If you try to tease out 3 classes with 4 variables, you get 1 degree of freedom. But here's a trap that many people fall into. They want to tease out 3 classes with only 4 binary variables, and it looks like you have a model that can be tested with 1 degree of freedom. But it turns out not to be identified because it has 1 indeterminacy. And Leo Goodman has written about that in a paper that we'll refer to later on. So if you want to tease out 3 classes, you better have at least 5 variables, because then you're fine. Then you're going to have a over-identified model that can be tested. Now, this is for exploratory factor analysis, exploratory latent class analysis, but there's also confirmatory latent class modeling, which applies various kinds of restrictions to the parameters in H0. And then just a comment on the fact that now we're going to try to get used to working on a logit scale in line with logistic regression. We're going to work with logistic regression in these latent class models. So we work with this probability expression. That's starting with the logit, going to the probability. In equation 82, we start with a probability and go to a logit. So here, 81 and 82 shows you how to go back and forth between probabilities and logits. So for instance, if you're going to do a simulation study, Monte Carlo simulation study, and you want to have 75% in class 1 and 25 in class 2, well, here's how you then compute the logits to specify that logit parameter. So for instance, if logit is 0, probability is 0.5. If the logit is negative, probability is less than 0.5. If logit is positive, it's greater than 0.5. If logit is very low, then probability is close to 0. If logit is very high, probability is close to 1. This very high and very low is going to be used to fix probabilities at 0 and 1, if you want to have a confirmatory type of analysis. All of these general topics will come back when we talk about the examples. Now, I talked about H1 and H0, and that relates then to trying to figure out if the model is suitable for the data. And very often, we're used to working with frequency tables or continuity tables, where you're familiar with the Pearson chi-square test. So this is chi-square a la Pearson, where you work with the O minus E squared divided by E. Meaning the observed frequency in the table. And so if you have 3 binary variables, you have a 2 by 2 by 2. You have an 8-cell table. And E is expected or model estimated. So E, you might write that E is the model estimated frequency. That is the frequency estimated under H0. O, by the way, is the observed, which is perfectly fitted by the H1 model, the unrestricted multinomial model. So one can think of O as E under H1, whereas E is the model estimator under H0. Now there's an alternative chi-square LR for likelihood ratio. It's both of them are chi-square, but LR comes from maximum likelihood theory, and it looks at the relationship between O and E through this equation, looking at how close they are through this equation, rather than how close they are through this equation. You know, this is a closeness measure between O and E that's different here. So, but in large samples, these come out to be similar, and as we will see, sometimes they disagree greatly, and when they disagree a lot, you probably shouldn't trust either one of them. The rest of this text you can ignore, but it just says that we can do this estimation and this testing also when some of the indicators have missing data. And we will also see shortly that these chi-square tests for the frequency tables have shortcomings. And we will point out that in those cases, we can rely on model fit to univariate and bivariate frequency tables. So if you have, say, 10 variables, instead of looking at the 10-variate table, you look at each of the bivariate tables, 10 times 9 divided by 2 bivariate frequency tables. And in Mplus language, that's looking at Tech 10. So with that, I think we have had enough of me talking theory. So here comes Linda with some application.
Okay. So the way that we're doing this, we're giving you a little theory, a little practice, a little more theory, a little more practice to try to break it up for you. So if you take a look at the table that's on both screens, what we're looking at here is the national study, as Bank said, from the NLSY, and it's on alcohol dependence criteria, or the variables that we're looking at. And we're looking at a latent class analysis. So the columns represent the 2-class solution and the 3-class solution for the latent class analysis, and the rows are the symptom items, the alcohol symptom items. So for example, withdrawal, tolerance, drinking a larger amount than you want to, not being able to cut down, et cetera. You can look at those. But the important thing here is to understand what we have. We have our structural parameters up here where we have prevalence. So the structural parameters are the class means, as Bengt had mentioned before, and the measurement parameters are in the boxes. These are the conditional item probabilities. So Bengt mentioned we have structural parameters and measurement parameters in the model. Measurement parameters being about the items and structural parameters about the people. If you look at the very bottom, you'll see that the likelihood ratio chi-square for the 2-class solution is very large, 1,779 with 492 degrees of freedom, whereas the likelihood ratio chi-square for the 3-class solution is much lower at 448 with 482 degrees of freedom. So we're going to concentrate on looking at the 3-class solution, the results from that. And just to mention, Bengt had mentioned we're in an exploratory situation here. So much like with exploratory factor analysis, you have an idea in exploratory factor analysis usually of how many factors you expect to find based on the items you're looking at, because the items were developed in a particular way. So the same thing holds true with latent class analysis. You probably from theory have some idea of how many classes you expect to find. So what you would do is the same as in exploratory factor analysis. You would do several analyses with a couple more classes than you expect, and a couple less maybe. So you look at a range, just like an exploratory factor analysis, and then based on what the data tells you about model fit, and also though, based on substantive theory, you make a decision about how many classes you think you have. And it's not always clear, and so sometimes none of the fit measures agree, and you have to base it on substantive theory alone. So none of these analyses are just crystal clear, and you don't just put the data into the computer and push a button and it comes out. You have to actually start the analysis in a simple way, understanding your data very well and your theory very well, and then your results will be meaningful. But without the careful analysis, the results, may have no meaning at all. So the results of the analysis really depends on the care that you take while you're doing it. So here we have we're going to focus here on the three-class solution. So first of all, the structural parameters. We have class 1 that has 75% of the people, class 2, 21%, and class 3, 3%. And if you look at the conditional item probabilities for class 1, you can see that they're all very, very low, with the exception of larger. So the only item that the people endorse to any amount at all is drinking more than they had intended in that class. So you might want to think about that class as being the normative class as far as alcohol behavior goes. And that makes sense because 75% of the people are in that class, and we know that we don't have 75% of the people in the population with severe alcohol problems, or we hope we don't. Now, class 2 has 21% of the people, and if we take a look at what the largest is, conditional item probability is also larger, but then also if we go down, we see that this major roll hazard is also large for that. So in addition to drinking more than they had intended, they're also perhaps drinking and driving. They're doing some behavior that's dangerous related to alcohol. Whereas class 3 seems to endorse all of the items to a fairly large extent. So you might consider that class 2 would be people who have problems with, who are referred to as alcohol dependent. No, what is it? Abusers. I can never get these substantive things down. Alcohol abusers, whereas the class 3 is actually a more severe alcohol dependent type of individuals. So here we have the results for the 2 classes and the 3 classes. The difference with the 2 class is classes 2 and 3 get put together, whereas they get separated in the 3-class solution, which from looking at the chi-square indicates that those 3 classes fit the data better. So that's the results of doing the latent class analysis. But then the question is, well, so why are, what's the big deal about this? I mean, so what do we do with this information now? Well, we could regress the latent class variable on a set of covariates and try to figure out, okay, what's different about the people who abuse alcohol? What's different about the people who are dependent on it and the normative class? And try to understand more about them that way. But usually what people want to do is they want to classify people, and they want to be able to say, okay, we have these alcohol abuse items, and we're having people answer them, and we want to know based on those answers, who are the people with severe alcohol problems? How many of these items do you have to endorse before you have a really big problem? And how many items can you endorse and still be considered to be normative in handling your life properly and dealing, in a good way with the use of alcohol? So what you might consider doing is what we show here on the left screen, and that's creating a variable called number of criteria met, which you can do in Mplus in the define command using the sum function, where you would just sum the 9 items, alcohol items, and get a sum score for each individual in the sample. So for the people who didn't endorse any of the items, they would get a sum score of 0. For those who endorsed one item, they would get a sum score of 1. And all the way down to those who endorsed all 9 items, they would get a sum score of 9. And let's concentrate once again on the 3-class solution. And you can, if you look down the columns, so for example, for class 1, you'll note that nobody endorses more than 1 item. And if you look down for class 2, the abusers, you see that one person endorses 1 item, but most of the others endorse 2, 3, or 4 items. 1 endorses 5, or 19 endorse 5. And then if you look down at class 3, you'll see that the majority have endorse 5 or more items. Only 2 endorse 4. So when you look down here, you can see that you can make cut points. So for example, you can make a cut under 1, another one under 4. And if you do that, then you have no misdiagnosis of normative. For the abusing class, 1 person does not get captured because they endorse only 1 item, and 19 don't get captured because they endorse more. They would be considered in the dependent class, and this one would be considered in the normative. And then you only misclassify 2 dependent people. So this is how people might use this in practice. They would say, okay, anybody who endorses 5 or more items is alcohol dependent. Those with 0 and 1 are normative, the others are alcohol abusers, and then base treatments on those 3 categorizations. So now Bengt is going to come back now, and here we decided on the classes based on only the chi-square. He's going to be discussing other ways that you can determine the number of classes, and then I'm going to come back and show you what those other ways pointed to in this data.
So this is actually corresponding to a real situation that was discussed or is discussed in the US. They're trying to come up with new ways of coming up with cut points for diagnostic criteria of substance abuse problems in the DSM-5, Diagnostic Statistical Manual, version 5, moving from 4 to 5. And then trying to decide how many criteria should you require to be fulfilled for being alcohol dependent. And this analysis that Linda talks about suggests 5 or more in this case. So it's a way of using latent class analysis to validate any decision on number of criteria fulfilled that they would like to use. So this would support 5 or more instead of, say, 6 or more or 4 or more. Now you may ask yourself, well, why do we work with number of criteria fulfilled? Why don't we just work with the latent class model from beginning to start? After all, it puts people into classes, and you can see how many alcohol dependent and how many alcohol abusers there are. Well, the answer is probably that the DSM-5 research group is not quite ready to rely that entirely on latent class analysis. But maybe it'll get there. But at least you could use it as a support, as an empirical analysis machinery to support any decision on cut point. And this is very easy to do. Like Linda said, you sum up the items to create that variable, and you create the most likely class membership to get the class membership variable. And then you just do crosstabs on it. So, and Linda will talk about how to get the most likely class as we move forward. So now I'm going to be switching you back. That was just a brief respite from theory, and here we continue. And now we're going to reveal that chi-square testing, the test that Linda showed you, that pointed to 3 classes instead of 2, is fraught with problems. That is, yes, it's designed to be an overall test against data, but given that we work with frequency tables with many cells, when we have many variables, we're going to get a problem with sparse cell counts. So even if you have 10,000 observations, when you have, say, 8 or more variables, binary variables, you're going to get many cells that have relatively small frequencies. And you remember from Statistics 101 that you're supposed to have what? Expected value in each cell at least 5, and then it got modified to at least a very small number of cells having less than 5 or less than 1. But in any case, it's true that the chi-squared approximation does not work well when you have a good number of cells with low or 0 cell count in the sample. Now that's testing against the data, and we'll talk about alternatives for doing that. But very often then you also try to figure out how many classes you have. That is not testing against data, but comparing models with different number of classes. The likelihood ratio chi-square cannot be used here. Chi-square testing can be used on nested models, one model being a special case of another model where some parameters are fixed at 0. That's chi-square difference testing, it's called, and that difference test follows a chi-square distribution under certain circumstances. But it cannot be used because, say if you test a 2-class model against a 3-class model, the 2-class model is a special case of the 3-class, but a special case where the probability for the 3rd class is 0. And that's a parameter that's on the border of its admissible space. And that's a bad thing. That makes the chi-square test invalid. And it's not only an academic matter, but it's actually makes a big difference numerically that the chi-square distribution is not followed at all. So given that we cannot do chi-square testing for trying to figure out how many classes there are, we use the so-called BIC that we talked about briefly before. Bayesian information criterion. And based on Bayesian reasoning, you come to this formula 81, which says that we go by the log likelihood value and a second term, which has to do with h, number of parameters, and log of the sample size. So what BIC accomplishes is that BIC would be good. A good BIC is a small BIC in this way of scaling it. A good BIC is a small BIC, and BIC is good when the likelihood is high. The likelihood is high, the 2 times log likelihood is high, and the minus 2 times likelihood is small. When the likelihood is high, BIC gets low, but only if you also have very few parameters. So this is a penalty for having many parameters. So you can obtain a good high likelihood trivially by just adding parameters, but you want to get penalized for adding too many parameters. So this is a counterweight. So if you add many parameters, BIC gets big and bad. And the number is number of parameters times sample size according to Schwartz theory here. So choosing models with smallest BIC is very common in mixture latent class models. And it's a reasonable approach, I think. But in Mplus, we also try to benefit from more sophisticated approaches. There is an approach that was published in Biometrica, a theoretical statistical journal in 2001 by Wong, Low, Mendel, well actually by Low, Mendel, and Rubin, drawing on result by Wong in econometric literature. And a typical statistical approach, that is, we're saying that the likelihood ratio, which is a ratio of the likelihood under 2 class and the likelihood of under 3 class, that ratio is not chi-square distributed. So one can give up and use BIC instead, but if you're a true theoretical statistician, you then ask yourself, well, if it's not chi-square, what is it? So Low, Mendel, and Rubin derived the distribution for that likelihood ratio test. So you can use it again. It's not chi-square, but it has a distribution and can give you a p-value. And that's what you get through Mplus Tech 11, technical output number 11. And another very, perhaps more commonly used in mixture modeling, it's when you don't know the distribution of something like a likelihood ratio, when it's not chi-square, you can always figure it out empirically by bootstrapping. And we'll tell you about that on the next slide. And that's Mplus Tech 14 that accomplishes that got introduced in version 4. And just briefly, talking about bootstrapping here, it's on your slide 76. So we create a likelihood ratio as 2 times the log likelihood for model 1 minus log likelihood for model 2, where model 2 is nested within model 1. So for instance, model 2 would be a 2-class model, and model 1 would be a 3-class model. And as it says here, when doing that kind of testing, the LRT, that quantity here, does not have a chi-square distribution due to these boundary conditions, probabilities at 0, but its distribution can be determined empirically by bootstrapping. And here are the steps. In your K-class run, 3-class say, estimate both the 3-class model and the 2-class model to get the likelihood ratio value for the data. And then in step 2, you generate data, artificial data, say 100 samples, using the parameter estimates from the, in this case, 2-class model, and then fit the 2-class and the 3-class model, 1 class too many, to compute this artificial data log likelihood ratio test for all of these 100 samples. And then you get a distribution of such test values. And it can look like this. So this is the artificially obtained bootstrap distribution. And the observed data likelihood ratio test has a value somewhere in this. And you can then figure out how far out in the tail it is empirically by looking at and getting, therefore, a p-value. So this is described in the Mplus User's Guide a little bit more fully, and in the literature like McLachlan and Peel more fully. But just to give you a flavor of this existing here in the program. The slides 78 and 79, we talk about how this is implemented in Mplus. I think it's a little bit too dry material to talk to you about now on the first day's morning. So I'll just leave you with these slides to know that they are here, but that they are described more thoroughly in the User's Guide, how to actually practically work with this bootstrap likelihood ratio test, Tech 14. And Tech 11 on slide 80, this text is from the User's Guide, so I've already described that. And I think I'll go to this instead. And I'll tell you a little bit about how we like to work with these procedures for determining the number of classes. So there's a simulation study which was part of Karen Nyland, my former student, dissertation, and it's published in the Structural Equation Modeling Journal. And all of these publications that has to do with us sit on the Mplus website, so you can take a look at it there under papers. And she found that bootstrap likelihood ratio test has a better type 1 error, you know, the probability that you reject the model when it's correct, than NCS being the naive chi-square, that is taking the 2 times log likelihood difference and pretending that it is chi-square, even though we know it isn't, right? So it's the wrong chi-square, naive chi-square. So bootstrap has a better type 1 error than the wrong way of doing it, and then the low Mendel-Rubin. And bootstrap likelihood ratio test finds the right number of classes better than BIC, the wrong way, naive way of doing it, and low Mendel-Rubin. So bootstrap seems to be theoretically the best. For instance, you have this case here. You have a latent class analysis of categorical outcomes. And you ask yourself, which % of the time do these different techniques pick the right number of classes? So you have the BIC approach, you have the naive chi-square approach, you have low Mendel-Rubin, which is Tech 11, and you have the bootstrap likelihood ratio test, which is Mplus Tech 14. Tech 14, Tech 11. And you have a 10-item complex 4-class latent class model. And the 3 rows are different sample sizes. And for instance, if you look at sample size 500, this says the correct number of classes is 4, and BIC picks the right number of classes for 76% of the time, but 24% of the time it picks too few classes. So the general finding is that BIC tends to underestimate the number of classes a little bit, particularly if you have a small sample. Then you're very poorly situated if you use BIC. If you have a large sample, you always pick the right number of classes according to this simulation. And the naive chi-square tends to pick too many classes too often, so you can see how the chi-square really doesn't work, right? For instance, at 500, the naive chi-square approach is a worse approach than BIC by far. Lomendal-Rubin does better than the naive, and maybe about the same as BIC, but when you get up to 1,000, it does not do as well as BIC. Bootstrapped likelihood ratio test does really well already at 500, does better than any of the other, and stays that well even at 1,000. So from this, you would suggest that bootstrapped Tech 14 is the best approach, but BIC is not too bad. Now, this is just simulations, and simulations are limited, and I would say that in my own work, I typically use BIC as a first stab at finding the number of classes, BIC together with substantive reasoning, and sometimes when I really want to adjudicate or choose between, say, 5 or 6 classes, where BIC is not totally clear about it, I go to the bootstrap. But people keep, this has become a cottage industry now to do simulation studies on this. So, and then lots are needed, so feel free to do more. All right, now these are, so we talked about all kinds of statistical machinery to guide you in terms of number of classes. They very often don't work that well in the sense that they very often don't guide you very precisely, as Linda will say and show in her examples. And that's probably because many of the variables that we analyze, many of the measurement instruments have not been designed well to capture latent classes. You know, we tend to analyze the variables that we have, and they weren't designed, they were not necessarily designed to find these types of individuals. So we can't expect there to be a clear signal in the data corresponding to this model. We cannot expect that. So very often we have to combine the statistics with substantive theory. What does your theory say? And what auxiliary variables can we relate the model to? Auxiliary, by that I mean variables not used in the analysis. So that could be background variables, concurrent variables, or later variables, talking about predictive validity. So decide on the number of classes that's useful for predicting something that happens later. Could be a way of determining how many number of classes you want to work with. On the right slide, we talk about quality of classification, which is based on those posterior probabilities at the end of the estimation once we've gotten maximum likelihood estimates of our parameters. And we will take a look at 2 ways. One is a classification table, which is described up here in the first sub-bullet, classification table, and I think Linda will have examples where she goes through discussing how to read that kind of a table. And if you want to summarize it into one single number, you talk about the entropy, which is this formula 84, where an entropy close to 1, it's a value between 0 and 1. Close to 1 indicates good classification. Many individuals have posterior probability values close to either 0 or 1. So they're unambiguously classified. I sort of go by the rule of thumb that if you have an entropy of 0.8 or greater, you are well off. You have a good classification going, and I will later refer to a recent paper which finds that 0.80 is a good cut point for other reasons too. Now, what we have on the right should not be thought of as a determining factor in terms of deciding on number of classes, but it is really instead talking about how useful is the model that you have. So if you come from the structural equation modeling world, you make a distinction between how well does the model fit the data in terms of chi-square or fit indices, and then a separate consideration is what is the R-square for various equations in the model. A high R-square does not mean that you have a well-fitting structural equation model. Neither does a high entropy say that that's the model you should choose, that's the best model that fits the data the best. Well-fitting models can have a very low entropy. So they fit the data well, but they won't be that useful.
Do you think I should do these 4 slides, or we should take questions? It's 10 to 12.
You decide.
Okay.
Go for it.
All right, we'll go. We'll try to do the next 4 slides before we take questions. So now what we're doing is we're going back to the example that we looked at earlier. Okay. So if you remember, we were looking at the alcohol example, and we looked at between 2 and 3 classes. We saw these are the numbers we looked at, the 1779 and the 448, the chi-square values. And based on that, we decided on the 3 classes. But now what we've done is we have number of classes, 2, 3, 4, and 5 for the columns. And for the rows, we have the Pearson chi-square, likelihood ratio, the degrees of freedom, the percent significant of residuals from our Tech 10 output, the log likelihood, number of parameters, BIC, Low-Mendel-Rubin test, Tech 11, bootstrap likelihood ratio test, Tech 14, and entropy. So just to quickly reason through what Banks said, when you have when the Pearson and likelihood ratio chi-square disagree, which they do in this situation, you can't really use either of them. So this is basically to be ignored. Now, when you have categorical items, you can use Tech 10, which is nice because we look at univariate, bivariate, and response pattern residuals. And here we're looking at the bivariate residuals, and we see for 2 classes, we have 84 standardized residuals that are greater than 1.96. For 3 classes, 4. For 4 classes, 1. Now, you have to remember the 1.96 really needs to be made larger in some way to take into account we're doing many tests, not just a single test, like Bonferroni correction type thing. So we probably wouldn't have as many here, or we would have more here based on that. So, but basically, I would think this points to the 3-class solution, looking at Tech 10. The log likelihood has a huge drop, or rather a huge rise between 2 and 3 classes, and then not so much. So that might point to 3 classes. The BIC actually hits a minimum, 539, 508, 535. So we hit a minimum for 4, so that points to 4 classes. The Low-Mendel-Rubin, we have a larger value here, which would point to 4. We don't have anything except zeros here. That doesn't help us. And as Bengt mentioned, entropy really isn't a fit statistic. So we sort of have 2 statistics that point to 3 and 2 that point to 4. So, what do we do? Well, one thing that we can do is then we can look at plots. So you can use the plot command in Mplus with the series option to create these item profiles. So here we have the 2-class solution. And then along this axis are all the items are listed. So like item 1, item 2, item 3, item 4, and then the conditional item probabilities on the y-axis. And you see we have the low class, the normative class, which is just drinking more than they wanted to. We have another class that has a couple of ones that are high. If you go to the 3-class solution, you have the same 2 classes, but in addition, a 3rd class of individuals who are higher on all of the items. The 4 class, you have the 3 classes you saw, and then a variation on the class that has the 2 items that are higher. And then when you go on to the 5 classes, it gets a little bit messier. So if you have to choose between 3 and 4, unless you had a huge reason to think that these 2 classes, this one and this one, the blue and the lilac, I guess, unless you had a real substantive reason for thinking these classes really are different and are going to have different predictors and different types of distal outcomes or something, then you might just say put them together and then go for the 3-class solution. So this is how you would reason about this. So none of these things have like a definite answer. It just comes out and says this is the answer. This requires a lot of analysis, a lot of thinking, a lot of considerations of whether, like Banks said, your data probably weren't actually developed for this type of analysis. And maybe you have to actually accept the fact that there's not enough information in this data to really answer the research question that you're trying to answer. And that's a sad point to come to, but it happens. So now we've gone through this example, we've gone through the results, and how did we do it in Mplus? Here's the input over here. And basically, we went over all these commands, so I won't bother with this, but here we have this is the key. Classes equals C3. This is for the 3-class solution. For the 2-class solution, you change that to a 2, and then for the 4-class, a 4, and for the 5-class, a 5. So all we did to get all the results that we're showing you is run it once with a 2, once with a 3, once with a 4, once with a 5. And here's the plot command that I referred to. So you say type equals plot 3, series equals U1 through U9, and the asterisk in parentheses more or less says it will create its own x-axis. And that's how we did it. And then one last slide before we take questions, and that's on looking at neighboring models. So we're going to be looking at a lot of different types of models this afternoon. But one way we could have looked at this is instead of a 3-class latent class model like we had, we could have looked at a 2-factor factor analysis model. That could be a neighboring model, another way that we might be able to represent the data that we're looking at. And if you look at the BIC, we know now these are not trustworthy, those log likelihoods. But if you look at the BIC is lower for the 2-factor factor analysis model than it is for the 3-class LCA model. And the way that we show this is we have the 2 factors, one on the y-axis, one on the x-axis, and the classes are represented. The green is the normative class, and the red is the dependent class, and the blue is the class of alcohol abusers. And so you can see that it's pretty clear the normative is lower on the factor, and the abusers in the middle and the dependent alcohol problems have the higher factor scores. And you also see that the factor scores are very well highly correlated and could perhaps represent one dimension. So this is another way we could represent the data, but it doesn't have the advantage that we can actually have the cut points of how many items. It's not clear how to make the cuts on here. So this is just to show you that we can consider other models, because as the afternoon goes on, we're going to be considering combinations of latent class and factor analysis models that give a unique way to look at this type of data. So then I think we should take questions and have lunch.
Let me just add also that this again corresponds to a big debate in psychiatric circles where they talk about dimensional versus categorical representations of mental health problems, where the categorical representation corresponds to classifying, diagnosing people as having a problem or not, and that is then directly related to the latent class analysis model, whereas the dimensional thinking is that problems are not either or, but a continuum, and that then corresponds to the factor analysis model. So it's very relevant for these kinds of analysis of diagnostic criteria to compare the LCA with the FA model, and we see that the FA model actually has, let me not shoot you in the eye, actually has fewer parameters, but still has a better likelihood. So it really seems like a better fitting model for these data, and that comes out in the BIC, of course, because BIC is doubly advantaged by higher likelihood and fewer parameters. But we'll tell you later this afternoon that we have an even better model in store, just to keep you
coming back.
That's right. So let's take questions then again. Yes? So the question is, how were the factors constructed in this example? And in this case, this is actually an exploratory factor analysis. Exploratory factor analysis of dichotomous items. So we impose no special loading structure, no fixed loadings, but just saying that we have two factors in this case, two factors fitting the data better than one factor. So this is an exploratory factor analysis for which we have then plotted the factor scores for the different individuals, or rather the different response patterns, and then we have overlaid the latent class membership on top of the factor scores to see their relationship. Yes. So the question has to do with analyzing psychiatric criteria. There seems to be often a finding of 4 classes, and is that a statistical artifact? Now let me ask you, what kind of application, what kind of outcomes are you looking at? In which kind of mental health area?
In relation to psychosis.
So looking at psychosis-related diagnostic criteria, you find 1 normative class and 3 non-normative classes. Yeah, I haven't seen that literature. In my analysis, it seemed to be a variation in the number of classes that are found. But maybe that's a function of the measurement instruments, and or, hopefully, that is the right answer. Okay. Okay, so the question is on slide 86. Linda went over how to use the various statistical criteria to decide on the number of factors. And let's just say that one more time a little bit more expansively. So BIC, you go by the lowest BIC, right?
By the minimum.
Yeah, by the minimum. Linda pointed to this as, so 4 classes. BIC would say choose 4 classes because that's the lowest BIC value. And the more complex situation is, say LMR here, it has a 0.082, which is a p-value greater than 0.05. And what that's a result. You want to say it?
No, I was just going to, no, that's okay, I'm waving my finger. Go ahead.
No, you can point at it.
Well, no, but what you're looking for is when a number that goes above 0.05, so you can reject the null hypothesis and choose the K-1 class model. And also, this is a minimum, not the lowest. So it goes down and up.
Yeah, minimum
for BIC, right.
So just to repeat, so in your analysis, in your run with 5 classes, you get this p-value. What that refers to is a test of whether or not K-1 classes, namely 4 classes, fit better than 5 classes. Or rather, can the 4-class solution, in your 5, I'll say that again, because it's complex. In the 5-class run, you get a p-value. The p-value is the answer to the question, how likely is it that a 4-class model is sufficient relative to the 5-class model? So when that is greater than 0.05 in your 5-class run, it says you should choose 4 classes. So that's the crux of the matter. And the same thing for the bootstrapped.
But we never
But for
get
the bootstrap, there's 0 throughout, so you don't get any help from the bootstrap log likelihood ratio test. And in my experience, that often happens, and I don't know why. Whereas in simulations, it seems to work very well. Yeah. So the question is, can you combine LCA and factor analysis in one model?
We'll be doing that.
Yep. That is
This
the factor
afternoon.
mixture analysis that we're going to do this afternoon.
We can't say too much or you might not come back. So.
We won't say too much about it now because then you might not come back. Okay, more questions? Yes.
Next slide. I'm not sure about the significant bivariate residuals. What's that?
Okay, so up here, bivariate residuals. I don't think Bengt went over Tech 10, but Tech 10 is an option in the output command, and what it gives you is univariate, bivariate, and response pattern residuals. And what that means is that for each bivariate table, since the multi-way table for the chi-square is too big and has too many sparse cells and can't tell us about model fit, then we go down in Tech 10 to univariate and bivariate. So the bivariate is 2 items at a time. And we look at the observed values versus the model estimated values and come up with a standardized residual. And then what we look at here are how many of the standardized residuals are greater than 1.96. So that's comparing the model to the data on a bivariate level.
Yeah. So it's a way to avoid the sparsity of the cells in these chi-square test, frequency table test. Yes, in the back. I think the question is there a minimum number of individuals that you should require to have in a given class?
When you have too few people in a class, there can be problems that if you want to have covariates to explain class membership, you can get no variability on covariates in the class, which is more aggravating than a problem, I guess. But also, it has to do with the power to, in your study, and really the only way to know about whether you have enough power and whether your class might be too small to do what you want to do with it would be to do a simulation study. And you can do that pretty easily in Mplus. But I don't know of any rules of thumb for class size. Do you, Bengt?
No, it's hard to say anything general about it. So the issue is if you have very few people in the class, you may wonder, is that just a happenstance, a fluke? If you have a class that is, it has to do with the class separation. For instance, if you talk about continuous variables, how different are the means of a variable across the classes, between the classes? And if a very infrequent class has a very distinct mean, it can be discovered even though there's a small percentage of people in that class, even for fairly small sample sizes. So it depends on how clear the signal is in the data. So it's hard to say anything general about it. But as Linda says, if you have very few people in the class, it's hard to then predict class membership using covariates. Yes, in the back there. So the question is, do the items have to be binary or can they be of other scale types?
No, they can be binary, ordered polytomous, censored, count, nominal, any of the variable types that we do in Mplus.
And any combination of those variable types. So we just start with the binary case to keep it simple here. Yeah, that's a good general question. If you have a group of individuals who endorse, say, all items or none of the items, you can actually specify if that's a substantive, if there's a good substantive reason for that subgroup, you can actually specify that in the model. In the confirmatory latent class analysis, you can force the probabilities to be 0 for endorsing any of the items and tease out that group of individuals. You can throw them away, but then you wouldn't be able to predict their membership by covariates, so you can keep them in the model. On the other hand, those who endorse none of the items are often very similar to those who endorse, say, one of the items, a very prevalent item. So it could be an exploratory class by itself. Now, if you have very few individuals, then we go back to the answer of the first gentleman. Okay, so you are thinking about how this analysis compares to a Poisson analysis? Yeah, if you're working with the number of criteria met, this would certainly be a good Poisson distribution. So this would be a variable that would be a typical Poisson or count exercise, be it Poisson or negative binomial. But here we're not interested, you know, if you look at, it's a good question actually, because it brings up the general issue. Do you have sufficient information in the sum of the items? That's what's assumed by the psychiatric diagnostic research group. But what we're saying is that that's treating all items as carrying the same weight. If you endorse 5 items, it doesn't matter which 5 items. But the analysis, the latent class analysis that we've done, it matters which item. So the sum of the item is not the sufficient information. It's each item pattern that carries information. So some items will carry more information for classifying an individual than other items. So I think that's the essential difference. And that you accomplish by taking a multivariate analysis approach with several dependent variables rather than just looking at the sum here. But if you did, it would indeed be a count analysis.
Right.
So the question is, how does sample size relate to how many classes you can tease out of your data?
I would think it would depend on the data, and you know, so you'd have to do some type of a simulation study.
I would say it really is a matter of how strong the signal is in the data. By that I mean how separate are the different profiles. So for instance, if we have, I'll just take a guess here. Oh, that's pretty good.
No. There.
If you have this, I think the data has one strong signal here. The data says this looks like 3 classes. That comes through, you know. These are 6 primary classes. The high on all, high on abuse items, drinking larger and drinking and driving, and then the normative. Here you just bring in little variations, and here even further little variations, and none of these may be interesting substantively. These are the 3 substantively meaningful classes. Those signals are clear. Those 3 profiles are very different. So I would think with those clear profiles, you could get away with a smaller sample size than if those profiles hadn't been so different. So it's really a matter of how distinct are the classes. And the simulation studies that have been done in terms of being able to recover the right number of classes and the parameter estimates often suggest with continuous items that it has to do with the mean difference. Mean differences that are at least 2 standard deviations apart between the classes, then you can get away with much smaller sample sizes than if you have, say, only 1 standard deviation apart. But it is really no general rule that can be given. We've had successful analysis, 2-class analysis for samples as small as 30. And I'm sure there are unsuccessful analysis that even with a sample of 500. Yes? So the question was, in our examples, the classes seem to be clean, but in your experience, there is a catch-all class where many people fall into. And is that a class of no activity or activity on all items?
It's a class including all those observations which cannot be allocated to one of the precise classes.
A class of individuals who cannot be allocated to the other classes. I must say I haven't seen that in my data analyses. What would happen if an individual doesn't fit very well into any of the classes, that individual will be having a posterior probability that makes it likely to be in several neighboring classes, but so the person, if there are 3 classes, for instance, maybe 33% likely to be in that class, 33% in that class, 33% in that class. So for that particular individual is not clearly classified in any of the classes, but in my experience, that doesn't mean that those kinds of individuals need their own class. I haven't seen that. So I would have to know more about it to say. You know, we will show you after the break with more and more extensive examples how you look at the posterior probabilities that are estimated. So what you have experienced now, just as a summary, I think we should go to lunch, is a lot of theory. So this was a heavy part, perhaps the heaviest part, but it gives a foundation that we will refer back to as we go forward. So if you have no more questions, let's meet back at 1 o'clock. Or where is it?
No, 1:30.
1:30. 1:30.